Just imagine a universe born from a singular state of infinite density and temperature, expanding relentlessly from its own heat. A theory supported by layers of observational evidence, the uniformity of temperature and density, the creation of cosmic structures, and the existence of the cosmic microwave background radiation. This is the hot Big Bang theory. Yet, some enigmas remain unresolved: the horizon problem, the flatness problem, and the monopole problem. And then comes along another theory to save the day: cosmic inflation, an early, rapid, and merciless phase of exponential expansion. But, if you think this is where our story ends, you're mistaken. There's yet another baffling question to be answered: the origin of it all. But, I won't reveal that just yet. Stay tuned, because the most intriguing part of this cosmic odyssey, you'll find out soon enough. What's up, my amazing and curious folks? Ready to unravel the mysteries of the universe together? I'm your host, Caesar, here on Curiosity Wonderland, and joining me is the ever-insightful Sonia. Remember, folks, hit that subscribe button and bell icon so you don't miss out on any of our fascinating discussions.
Hi there, curious minds. Can't wait to dive into today's topic with you all.
Now, one of the biggest questions, perhaps the grandest of them all, that we can ask about our universe is where it originated from. Before the stars and galaxies, before atoms came into being, before the very first moment of time ever passed, how did it all begin? Quite a brain teaser, isn't it?
Absolutely. It's something many of us wonder about, and despite all our scientific advancements, we still don't have a definitive answer that's backed by measurable data.
That's right. But it never hurts to dive deep into these big questions, take stock of our current knowledge, and ponder the mysteries of the universe. In this quest, we need to consider three key concepts that people often mix up: the hot Big Bang, the theory of cosmic inflation, and the ultimate beginning or origin of the universe.
And understanding the dissatisfying answers that Big Bang and inflation provide for the ultimate beginning of the universe, that's a whole other layer of complexity.
You're spot on. Let's start by discussing the hot Big Bang. In the early 20th century, some groundbreaking pieces of information came together in an innovative way. Theoretical physicist Alexander Friedmann showed that a universe uniformly filled with matter and energy cannot be static and stable within Einstein's general relativity. It must either expand or contract.
And the rate of that expansion or contraction is determined by the energy density of space. So, what we have here is the beginnings of a theory that could explain the universe's origins.
Yes, and then we have three crucial pieces of observational data that supported this theory. It's a fascinating story of scientific discovery, and it all starts with a hot Big Bang. But that's just the beginning. Moving on, let's talk about some key observational developments. Henrietta Leavitt established a relation between the cycles of brightening and dimming of Cepheid variable stars and their inherent brightness. This came to be known as the period luminosity relation.
Then there's Vesto Slipher's work. He measured how light is shifted from our perspective within the solar system of these so-called spiral and elliptical nebulae, before we even knew they were galaxies. He discovered that they must be moving away from us at an incredibly fast pace, up to thousands of kilometers per second.
Exactly, and then Edwin Hubble, along with Milton Humason, started identifying variable stars, similar to the ones Henrietta Leavitt had studied, in those spiral and elliptical nebulae. This allowed us to measure their distances and confirm that they were indeed galaxies beyond our own.
And all these pieces of the puzzle led us to the concept of an expanding universe. As space expands, the matter within it dilutes to lower densities, and the universe becomes less dense over time. For radiation, like light waves, the energy dilutes and also stretches as space itself expands, causing the universe not only to expand and dilute, but also to cool.
So, running the clock in the other direction, we find that the universe, when it was younger, would have been more dense and hotter. It's really awe-inspiring to think about the evolution and the expansion of the universe over billions of years. Wow! This world of curiosities never ceases to amaze, does it? So many discoveries, so many records, so many mind-boggling facts. It's almost surreal. What do you think, my audience? Are you enjoying this journey through the cosmos? Don't forget to hit that like button if you're loving these astronomical revelations as much as I am. If we go farther back in time, all the matter and radiation would have occupied a smaller volume, which would make the universe denser. The light that was stretched by cosmic expansion, if you run the clock backward, would have had its wavelength shortened in the past, leading to hotter conditions and higher temperatures.
That means, if we imagine going all the way back, as far as the laws of physics will let us, we'd end up at a singular state, where all of the matter and radiation were contained within a single point of infinite density and temperature. A raw beginning where everything that now shapes our universe was condensed into one singular point.
Exactly. This original notion of the Big Bang leads to 5 cornerstone predictions of the theory.
Let me guess, the universe should be expanding, cosmic structures like stars and galaxies should form over time, it was hotter in the past, atomic nuclei couldn't stably form, leading to the prediction of relative abundances of light elements, and the universe was once so hot that neutrinos played an important cosmic role.
Bingo! With strong observational support for all 5 predictions, the Big Bang remains unchallenged as our leading theory of the early universe.
Just imagine, the universe once being so hot that neutrinos, those tiny particles that hardly interact with anything, played a significant role. It's certainly a testament to the extreme conditions of the early universe.
The temperature and spectrum of this radiation has now been measured, and the agreement with the Big Bang's predictions is extraordinary. However, even as evidence was accumulating for the hot Big Bang in the 1960s and 1970s, puzzles emerged as well, things that were observed, but that the Big Bang itself couldn't explain.
Could you elaborate on these puzzles?
Sure, there are at least 3 observations that simply don't make sense if we start from the premise that the universe began from a singular state of arbitrarily high temperatures and densities. The first is the horizon problem, which questions how different regions of the universe that never had time to communicate or exchange information since the start of the Big Bang came to have the same temperature and conditions.
Right, and then there's the flatness problem. How did the universe find this delicate balance between the initial expansion rate and the gravitational effects to result in an exactly spatially flat universe?
You hit the nail on the head. Then, the third puzzle is the monopole problem, which questions why, if the universe reached arbitrarily high temperature and energy conditions, there are no leftover heavy relics like right-handed neutrinos, magnetic monopoles, and other particles that should be observable and left over today.
So, these puzzles suggest that the Big Bang theory alone is missing something. Is there a mechanism proposed to explain these?
Yes, in 1980, Alan Guth proposed that an early, rapid, and relentless phase of exponential expansion, where the universe's energy was not distributed among matter and radiation quanta but was inherent to the fabric of space itself, would solve all 3 of these problems. The reason for the universe having the same temperature and density everywhere can be attributed to things being causally connected in the past, and then, stretched to be far apart by this early expansion phase. The universe appears flat today, because regardless of how it started off, inflation stretched things so that the part visible to us appears indistinguishable from flat.
So, in essence, the universe never reached arbitrarily high energies or temperatures, just the maximum temperature that was achieved in the aftermath of the end of inflation?
That's correct. Inflation provided a mechanism by which these 3 observables could be explained, offering a powerful alternative to the standard hot Big Bang. What's interesting is that inflation would provide a quantum mechanism for seeding the universe with initial imperfections, or the seeds of cosmic structure, that would later become observable in detail.
So, the quantum fluctuations inherent to space, which were stretched across the universe during cosmic inflation, gave rise to the density fluctuations imprinted in the cosmic microwave background, which in turn gave rise to the stars, galaxies, and other large-scale structures in the universe today?
Absolutely. This is the best picture we have of how the entire universe behaves, where inflation precedes and sets up the Big Bang. The sad part is, we can only access the information contained inside our cosmic horizon, which is all part of the same fraction of one region where inflation ended some 13.8 billion years ago.
That's incredible. Inflation made testable predictions about the seeds of cosmic structure that should appear in both the cosmic microwave background and also in the large-scale structure of the universe, as well as setting a cutoff for a maximum temperature that ought to be observed. And these predictions were borne out by observations made from the 1990s to the present.
Inflation represents an exponential expansion of space. It sets up a very different picture of the beginning, not a singularity like the original model for the Big Bang, but a whoosh that led to a Big Bang. In an inflationary scenario, we never reach a singularity, where space goes to a singular state. Instead, it can only get arbitrarily small in the past, while time continues to go backward forever.
So, does this mean there isn't a true beginning to the universe?
Well, that's a really big question. When we were only considering the hot Big Bang without inflation, we could extrapolate back and reach a singular state where the size of the universe would go to zero in a finite amount of time. But because inflation expands space in an exponential fashion, it's impossible to extrapolate it back to a singularity.
So, what you're saying is, with exponentials, it would take an infinite amount of time to go back to a state where the universe had zero size.
Exactly. And to make matters worse, the observable evidence that we have for inflation is confined to only about the final 100 or so doublings of the universe before inflation ends. This corresponds only to a time period of about the final 10 to the power of negative 32 seconds before inflation ends and gives rise to what we know as the hot Big Bang.
If we were hoping that we could just push off a singular beginning to an earlier epoch, does this mean inflation squashes that hope?
Essentially, yes. There is nothing we can observe that tells us anything about what, if anything, gave rise to inflation. During cosmological inflation, the space contained in the inflationary region grows exponentially, doubling in all three dimensions with each tiny fraction of a second that passes. When inflation ends, a hot Big Bang ensues. But due to quantum effects, each region where a Big Bang occurs will be surrounded by more inflating, exponentially expanding space.
So, no two regions where hot Big Bangs occur ever collide, intersect, or overlap?
That's right. And that brings us to a fascinating aspect of inflation called eternal inflation. Any model of inflation you construct that works causes the universe to expand in such a way that inflation ends in some regions, leading to a hot Big Bang. But there will be infinitely more, surrounding regions where inflation continues.
So, the inflationary state will persist eternally into the future?
Exactly. And sporadically, due to quantum fluctuations, there will be individual regions where inflation does end and a hot Big Bang ensues. However, these regions will be vastly outnumbered by regions where inflation never ends.
I see. So, no two independent regions where Big Bangs occur will ever overlap?
Precisely. The inflating universe drives them apart. However, even eternal inflation has its limits. It's only eternal to the future, not to the past. Inflationary spacetimes are not past time-like complete, and must have emerged from some prior, non-inflationary state.
So, one of these bubbles, where inflation ended, gave birth to our universe?
Yes, some 13.8 billion years ago. However, it is unknown what spawned the state of inflation. It couldn't be eternal to the past.
And bouncing or cyclic cosmologies, they don't provide a way out of this conundrum either?
Indeed. These alternatives have been shown to suffer from the same problems. We've navigated through a lot of cosmic concepts today, but it's essential to remember that these theories aren't sufficient to tell us the universe must have begun from a singularity. It may have, but it's not a necessity. You can easily design a past time-like complete spacetime where inflation occurs by modeling the scale factor of your universe as a growing exponential plus a constant rather than a pure, growing exponential on its own.
So, while the hot Big Bang is our best description of our early universe, it wasn't the very beginning?
That's right. There's a cutoff in how far back you can extrapolate the temperature and density of our matter and radiation-rich universe. Before the hot Big Bang, there was a period of cosmic inflation, which set up and gave rise to the hot Big Bang. This period of inflation couldn't have gone on forever, and must have arisen from some pre-existing, non-inflationary state.
But we don't know much about this pre-existing state, do we?
Unfortunately, we can say very little about it, except for the large number of things that we can firmly state it couldn't have been. As much as we'd love to give an answer to the question of a first cause for existence, the truth is that we don't yet know how, or even if, things truly began. This is science at the frontiers, and our understanding of our cosmic origins is continuously evolving.
It's fascinating how much we've discovered, and how much is still unknown.
Absolutely. And who knows, perhaps some young person listening to this podcast today will someday lead us to the next revolution concerning our cosmic origins. Today, we've journeyed from the hot Big Bang, through cosmic inflation, to the very edges of our understanding of the universe's origins. We've learned that while these theories provide the best descriptions of our early universe, they are not the true beginning. Faced with the vastness of the universe, we are reminded of how much we've discovered, and yet, how much is still unknown. This is science at its most profound, constantly unearthing new mysteries as it unravels old ones.
It's been a fascinating journey. Thank you for joining us on this cosmic exploration. If you've enjoyed this episode, please blast the like button, make a comment, and share this episode with your friends.
Absolutely. And remember, future scientific advancements may lead to new insights about our universe's origin. Who knows? The next revolutionary idea could be just a thought away.
So keep wondering, keep questioning, and keep exploring. Until next time, thank you for tuning into Curiosity Wonderland.
Goodbye, everyone, and stay curious. This cosmic exploration was inspired by the article Ask Ethan, How Did the Universe Truly Begin?, written by Ethan Siegel, published on Big Think on October 27, 2023. If you're keen to explore more about the topic, the full URL is in the video description. Now, it's time for me to blast off.